This is a brief introduction to neural networks. So, neural networks, like the brain, maybe we can use mathematical functions to map a given input to our desired output. A neural network is the name that is given to the neural structure or the natural structure of animal brains to describe how the cells in the brain or neurons exist together and communicate. So it's a complex, highly interconnected network of neurons that make up animal brains. The neural network involves many active neurons that are connected to other neurons through chemical signals. Once a neuron receives a chemical signal from the other neuron in the network, it then will accumulate a chemical potential. That potential will eventually activate the neuron, which will then in turn send the signal to the other neurons in the network. So if you look at this diagram, what we see here is that we have an input layer, which in our case will be our X variables. And then we have a hidden layer, and then we have our output layer of what we're trying to predict. An artificial neural network is a computer model of naturally occurring neural networks. These models were originally fit using a technique known as backpropagation that will adjust the strength of the connections through multiple iterations to reduce the error of the model through predictions based on the training set. And if you look at it, the model will simulate active neurons within the nodes. The connections are going to be represented by inputs and outputs. The nodes are going to be organized in a hidden layer between the predictors, our X's, and our responses, or our Y's. And then the inputs are connected to outputs through an activation function. Artificial neural networks have been successfully applied to many situations, including image and handwriting recognition, and as well as our recommender systems. They tend to overfit the data, so the use of cross-validation is highly recommended to monitor your performance with increasing model complexity, as well as using a penalty parameter. An artificial network can model one or more continuous or categorical response with one or more continuous or categorical predictor. An artificial neural network is a flexible model when our linear models might not perform as well. And this allows it to achieve lower bias without more variance. The neural network can be profiled to understand how the predictors are related to the responses, and an artificial neural network does not exhibit the same relationship as you would find with linear models, as we'll see when we go through some more examples. So now let's look at the structure of an artificial neural network model. Every predictor is an input into every node. So here we are looking at the Titanic data set where we are using passenger class, sex, and fare as the predictor variables to try to predict whether the individual survived. So each of these variables is an input into every node. And so in this case, we have 3 nodes and 1 hidden layer. So this is our hidden layer here. The activation function is calculated for each node. So in this case, each one will have an activation function. In JUMP, you can apply a second hidden layer. So this is an example of a 1 hidden layer neural network. But you can have 2 or more. And in those cases, you start getting into deep learning. The deeper layers of a neural network are typically computing more complex features of the input than the earlier layers. So in the JUMP platform, they tend to cap it at 2 hidden layers, but in theory, you can have as many nodes as you would like within these layers. This is just going to be an example of when we are using a single categorical response, which would be survive, with 3 predictor variables and a single hidden layer with 3 nodes. Now let's talk about the activation function a little bit. It's also called a transfer function or function G. The activation function provides the output for each node. The default activation function is going to be a nonlinear function. The function that's going to be the default here will be the sigmoidal hyperbolic tangent, or tan that performs all arguments between the -1 and +1. So this is the tan function that you see here. And then the tan is centered and created as a skilled version of the logistic function. So note that in JMP, the linear and Gaussian activation functions are available. It can be a linear function, an exponential function, or a logistic function as well. But the logistic and hyperbolic tangent functions tend to be the most common ones that are used. So let's look at what this tan function looks like in a chart. So a nonlinear hyperbolic tangent function has a domain of negative infinity to positive infinity with a range between -1 and 1. So this is what the plot of the tan activation function would look like. Now let's look at the artificial neural network model and specifically at the inputs to a hidden layer node. So again, what we have here is a linear combination of weighted inputs, our x's. These are the arguments that go into our tan function, which then becomes the output for each node h. So again, here we are looking at the same example where we have 3 predictive variables for passenger class, sex, and fare, where we are trying to predict whether someone survived. When I come up with a prediction, or hi over here, we can use the activation function, which by default should be the tan, and then we use our bias estimate portion so that we can have our weight estimates for each of our x values. So again, each of these nodes are comprised of each of these 3 different perspective variables that are weighted differently. And so in this case, we have 3 nodes, and we are coming up with these 3 over here. And then we are combining these hidden layer nodes to our final prediction for survival. And so this is what the function would look like. In summary, what we have here is a linear combination of the predictors, which is the argument to the activation function in each node. The parameter of the weight estimates for the linear combinations are unique for each node. The activation function normalizes the output for the nodes before they are combined into the response variable. So, if we were to initialize the weights and the bias is to be 0, each neuron in the first hidden layer would perform the same computation. So even after multiple iterations of the gradient descent, each neuron in the layer would be computing the same thing as the other neurons. Now let's talk about the function that is applied to the response. For a continuous variable, it's going to be a linear combination of the hidden layer nodes. For a categorical response, it's going to be a logistic function of the hidden layer nodes. So we are just talking about how we are getting from the hidden layer node out to our final prediction, which is the case of the survivor is a binary outcome. You either survived or you did not. We would be using a categorical response, which is going to be a logistic function of the hidden layer node. So let's continue looking at a response. What we are doing is we have a linear combination that's going to be used to relate the output of the hidden layers to the logit or categorical response. And again, here survive is a categorical response. So we are going to be using a logit combination. There's going to be another set of parameters or weights to finally combine the results from all of the activation functions as a model for our logit. It's the same as performing logistic regression using the hidden layer nodes as a new predictor variable, except that all of the weights are estimated simultaneously. So this is what the function would look like for us to come up with our final prediction for survived. So when you look at the JMP output, this is what you would see. So this example shows an example of parameter estimates for a hidden layer with 3 nodes. And the example is for the predictors from the cleansed marketing database dataset. And here we're using dem age, dem gender, and dem homeowner to try to predict the categorical variable target B as our output. The parameter labeled h number underscore another number refers to the parameter for node n. In this case, it would be for node 1 in the hidden layer. The first 5 parameters in the example that we see here, which are labeled h1 underscore 1, are for the linear combination of the first node. So the first 5 are in the first node. The next 5 are looking at the second node, and then the next set are the third node. Now the last four parameters in this example are for the linear combination of the logistic response, or the log odds. So here's our final one that is combining them into our final prediction for target B. One thing we will see when we actually perform this in JMP is that the cross-validation is not going to be an option for you to apply using the JMP platform. But we should still use validation, although not cross-validation, just to make sure that our results are not overfitting and that they will generalize well to new data. One of the other things you will see within the JMP package is that you have an opportunity to impute missing values. So by default, rows with missing values will be ignored. And so you can use this informative missing checkbox, which is going to be in the dialog box. And it does the following. For a continuous predictor, it replaces missing values with the mean of the variable and also a missing value indicator name with the column name. Whatever the column is that is missing will be included in your model. So you will get a new column name, and then column name is missing to indicate what the missing value is. For categorical type of predictors, the missing values are treated as the second level of that variable. So if you have three classes normally, but you have a missing value, you're now going to have a fourth class which will represent your missing data. And now, as far as the output that we get, here's an example of what you would see. So we would have our results for our training data set and then our validation set. So many of the same measures are going to be provided as what we saw with the logistic regression, as well as for decision trees and generalized linear models. Now we have the ROC curve as well as a lift curve that we can look at to assess how well the model performs. Then you have the confusion matrix as well as the rates. So here we can automatically see the actual yes that was predicted as yes with our sensitivity. And so here our sensitivity was 64.1% and our specificity here was 88.5%. So again, this output is very similar to what you have seen in the past.